You think you understand something. Then one day you pull on a loose thread, and the whole sweater unravels. Here's the thread I want to pull today. Why does math describe reality? Not how we use math, not what equations look like. Why, at the deepest level, does the universe obey mathematical rules at all? Why should it? It didn't have to. And here's the thing nobody tells you. We don't know. We genuinely, completely, embarrassingly don't know. And I've spent enough time with this question to believe that not knowing is the most interesting place you can possibly stand. So let's stand there together. Everyone assumes math is a tool we invented, like a hammer. We built it, we swing it, things get built. That's the story. Math is a human language we developed to describe what we see. But then you look at what actually happened, historically, concretely, and the story falls apart. Mathematicians in the 1500s invented something called complex numbers. Numbers that involve the square root of -1, which doesn't exist. You can't have negative area. You can't hold a square root of -1 in your hand. These were pure fantasy. Numbers for a game no one was playing, describing nothing in physical reality. 400 years later, 400 years, quantum mechanics comes along. And it turns out the wave function, the thing that describes how particles actually behave at the smallest scales we've ever probed, is written entirely in complex numbers, not approximately, not metaphorically, literally. You cannot write down quantum mechanics without the math that someone invented as an abstract game in the 1500s. That shouldn't happen. In the 1800s, mathematicians started playing with curved space. They asked, what if the rules of geometry were different? What if parallel lines could meet? What if space itself bent? This was pure intellectual play, no application, no experiment, just mathematicians being curious in rooms with no windows. Then Einstein comes along and says, that's it. That's the actual shape of the universe. Space-time isn't flat, it curves. And the math those 19th century dreamers invented for fun, it was waiting, ready, like it knew. How does that happen? How does a human being sitting alone with paper and imagination stumble into the geometry of the cosmos? I'll tell you what I think. I think we have no idea. And I think that's the beginning of something worth understanding. Let me give you 3 examples, concrete ones. Because this mystery isn't philosophical hand-waving. It shows up in real physics, in real equations, and it keeps showing up. First one, gravity. Gravity falls off with distance according to a very specific rule. It goes as 1 over r squared, where r is the distance between 2 objects. Not 1 over r to the power of 2.1, not 1.9, exactly 2. Why? Nobody knows. But here's what we do know. If that exponent was slightly different, planetary orbits wouldn't be stable. Earth would spiral inward or drift away. The precise number isn't explained by anything deeper in our theory. It's just true. And it's exactly the number that makes life possible. You could call that a coincidence. I'd be careful about that word. Second example, Maxwell's equation. In the 1860s, James Clerk Maxwell wrote down a set of equations to describe electricity and magnetism. He wasn't thinking about light. He was just trying to unify 2 forces. But when you work through the math, when you manipulate the equations the way a mathematician would, something falls out that he didn't put in. A speed. The speed at which electromagnetic disturbances travel through space. And that speed, the one hiding inside the math, invisible until you look, turned out to be the speed of light. Maxwell didn't discover that light was electromagnetic radiation through an experiment. The math told him. The equations were hiding something, something true, something nobody put there. Third example, Dirac. In 1928, Paul Dirac was trying to write a quantum equation for the electron, one that was compatible with special relativity. He wrote the equation, and the math handed him back two solutions. One was the electron. The other looked like nonsense. A mirror image, opposite charge, same mass. Didn't match anything known. Most people would have thrown it away. Dirac followed the math. 4 years later, Carl Anderson found it in a cloud chamber, the positron, the first particle of antimatter. It existed because the equation said it had to. Now notice the pattern. Every single time. The physicist doesn't find the phenomenon and then find the math. The math leads. The math points. The math knows something the physicist doesn't, and the physicist has to run to catch up. That's not a tool. That's something else entirely. Now look, I want to be honest with you here, because I hate when people skip the hard objections. Maybe we're fooling ourselves. Maybe math works because we built it to work. We tried 1,000 equations, threw away the ones that didn't fit, kept the ones that did, and now we act surprised that our surviving equations fit reality. That's selection bias, not mystery. This argument sounds reasonable. I've heard smart people make it. And I don't think it's wrong exactly. I think it's incomplete. Because if that were the whole story, math should only describe what we've already observed. It should fit the past and fail at the edges. It should not predict new things we haven't seen yet. But it does, constantly. The positron wasn't a known thing that Dirac fit an equation to. It was an unknown thing the equation demanded. You can't explain that with selection bias. Second objection. Maybe the universe is just simple underneath, and math is how simple things look. Simplicity naturally generates patterns. Patterns look mathematical. We're just noticing structure that was always there. I have some sympathy for this one. But then, quantum mechanics. Quantum mechanics is not simple. It is bizarre. It is counterintuitive in ways that seem almost deliberate. Particles don't have definite positions until you look. A single electron goes through two slits simultaneously. Measurement changes what's being measured. This is not simplicity. This is madness. And yet the math, the strange, abstract, probabilistic math, fits it with a precision that's almost offensive. So no, I don't think we're fooling ourselves. Something genuinely strange is happening. I just don't know what. Here's something that doesn't get talked about enough. What physicists actually do. Because it's weirder than most people realize. You'd think the process works like this. Observe something, find math to describe it, test the math, done. And sometimes it does work that way. But at the frontier, at the edges where nobody knows anything yet, the process is almost the opposite. Physicists start with mathematical symmetry. Here's what that means. A symmetry in physics isn't just an aesthetic thing, it's a structural one. It means the equations stay the same even when something changes. If you rotate your experiment in space and the laws still hold, that's a symmetry. If you run your experiment tomorrow instead of today and get the same result, that's a symmetry. And here's where it gets beautiful. There's a theorem, proved by Noether in 1915. And what it says is this. Every symmetry in physics corresponds to a conservation law, every single one. The fact that the laws of physics are the same in all directions, that symmetry, directly produces conservation of angular momentum. The fact that the laws don't change with time produces conservation of energy. These aren't separate experimental discoveries, they're consequences of mathematical structure. You don't find the conservation law and then wonder where it came from. You find the symmetry, and the conservation law comes free, like a gift from the equation. And modern physics goes further. The particles, electrons, quarks, photons, they're not fundamental little balls sitting in space. In quantum field theory, they're excitations of fields. And the fields themselves are what they are because of symmetry requirements. The photon exists because of a particular symmetry in how we can write down electromagnetic theory. The W and Z bosons, the carriers of the weak force, were predicted from symmetry before they were ever detected. We found the particles by following the math, by asking, what does the symmetry require? That's not using math as a tool. That's using math as a compass. And the compass keeps pointing somewhere real. Now I want to say something uncomfortable. and I want to say it carefully. We have names for the mystery. Smart people have built philosophical frameworks around it, and I genuinely think, the names make it harder to see clearly. There's something called mathematical Platonism. The idea that mathematical objects, numbers, geometric shapes, equations, are real. Not in the way a chair is real, more real than that. The chair might rot or burn. The number 7 doesn't. It exists outside of time, outside of space, independently of whether any human mind thinks it. And the physical world is, in some sense, a shadow of the mathematical world. Max Tegmark, a physicist I respect, has a modern version of this. He calls it the mathematical universe hypothesis. The universe isn't just described by mathematics. It is a mathematical structure. We're not finding math in nature. We're mathematical objects looking at ourselves. Maybe. It's an interesting idea. But I want you to notice something. That's not an explanation, that's a description, with more confidence than it deserves. Saying the universe is mathematical explains why math works in the same way that saying fire is hot because of its heat explains burning. You've taken the thing that needed explaining, put it in a box, written a fancy label on the outside, and called it done. I'd rather say I don't know than do that, because at least I don't know leaves the door open. There's a story I think about. Someone asks me, why do magnets repel each other? And I say, well, there's a magnetic field, and like poles push, and the field carries the force. And they say, but why? Why does the field push? Why does space transmit force? And eventually you hit bottom. Eventually you say, this is how it is. This is the rule. I can tell you what happens. I cannot tell you why there's something to happen at all. That bottom is real. Every explanation has one. And naming the mystery doesn't fill the hole, it just covers it with a rug. I'd rather look at the hole. Here's the part that genuinely unsettles me. And I mean that, not as a rhetorical device, actually unsettles me. If math describes physical reality this precisely, what does that say about us? Our brains evolved. Natural selection shaped them over millions of years to do specific things: find food, avoid predators, navigate social groups, throw objects at roughly the right angle. Evolution doesn't optimize for truth. It optimizes for survival. There's no survival reason to understand quantum field theory. There's no adaptive advantage in grasping the geometry of space-time. And yet, here we are, sitting down with symbols on paper, writing equations that have no obvious connection to spears or food or danger, and then going outside and finding that the universe obeys those symbols. Why can we do that? Two possibilities, and neither one is satisfying. First, we got lucky. Evolution stumbled into general-purpose reasoning as a side effect of solving simpler problems. The same cognitive tools that let us predict where the antelope would run turned out, accidentally, luckily, to be powerful enough to predict where the electron goes. We're accidents who happen to be capable of this. Second, the universe is structured in a way that makes it legible. Not to everything, not to bacteria, but to systems that are complex enough, curious enough, organized in the right way. The universe reveals itself, like it's waiting to be understood, like understanding is built into the architecture. I don't know which of these is right. I'm not sure either one is satisfying. The first makes our understanding feel fragile, an accident that could have gone differently. The second has a strange flavor to it, almost like purpose, which makes a physicist nervous. But here's what strikes me most. Math doesn't only describe particles and forces. It describes music. The intervals between notes that sound harmonious correspond to simple mathematical ratios. It describes economies, not perfectly, but the structure is there. It describes the logic of language, the patterns of population growth, the branching of trees, the spirals of shells. The same wave equation that describes light describes water. The same exponential function that describes radioactive decay describes compound interest. What is math touching? It's not physics specifically. It's not nature specifically. It seems to be describing something underneath, some deep structure that shows up in every domain where there's pattern at all. And we don't know what that something is. I want to leave you somewhere honest. People hear a question like this and they expect a reveal. They expect me to say, here's what's really going on. Here's the answer the textbooks don't tell you. Here's the thing. I don't have that. What I have is this. We possess a key. We've had it for a few centuries. It opens every lock we've tried it on. Atoms, stars, black holes, the moment after the Big Bang, the behavior of particles so small they have no position until you look. Every door, the key opens. And we have no idea what the key is, where it came from, who or what made it, why it works at all. We've used it to build transistors, which became computers, which became everything you're watching this on. We've used it to predict the existence of particles before we could see them. We've used it to understand the first 3 minutes of the universe's existence. The key works spectacularly, embarrassingly, almost insultingly well. And still, no idea what it is. Maybe the universe is mathematical, really mathematical, all the way down. And what we call physical reality is just one way a mathematical structure can be experienced from inside. Maybe that's true. I hold it open. Maybe we're mathematical. And when we do mathematics, we're not discovering something external. We're recognizing something we're made of. Looking in a mirror we didn't know existed. Maybe the question itself is wrong. Maybe asking why math describes reality is like asking why is the universe shaped the way it is? And the answer is just, well, it is. And you're here because it is. And that's all there is to say. I don't know. But here's what I do know. A human being, a creature evolved on one planet, made of star stuff, with a brain that fits in 2 hands, can sit down with a pencil and write marks on paper. Marks that refer to nothing visible, nothing touchable, nothing that physically exists. Pure structure, pure relation, pure form. And then that human can go outside, look at the sky, look at the atom, look at the bend of light around a massive object, and find, not approximately, not roughly, not kind of, find that the universe is following those marks. That is the strangest fact I know. I've thought about this for a long time. I've seen a lot of strange things in physics, and every time I come back to this, the unreasonable, unjustified, inexplicable precision with which the universe obeys human mathematics, I feel the same thing. Something close to awe, and something close to vertigo. Because it means either the universe is smarter than we think, or we're deeper in it than we realize. And I genuinely don't know which. We should be more amazed by this than we are. Most people walk around knowing that E equals mc squared and thinking, yeah, physics is clever, interesting stuff. They don't feel the weight of what it means. That equation came from paper, from thought, from a human mind trying to make things consistent. And then reality, without being asked, without being consulted, turned out to agree. That's not a detail. That's not a footnote. That's the central mystery of why science works at all. And it's wide open. Pull the thread. Let the sweater unravel. Because what's underneath, nobody knows yet. And isn't that something?